All right, so you remember the log button on your calculator? We proved last week that it's not a base 5, so our goal today is to figure out what the base actually is. So using our log button, we're going to fill out a table, see if we can find that pattern. Since I don't know exactly how wide to make it, I'm going to do a couple random negative numbers and see where that gets me. So over to my calculator, that log button's on the left side there right next to my 7. So if I press log, -5, it tells me a non-real answer. So that means I have no solution there. Now complete the table by picking a few positive integers as well. So you can see I chose 1, 2, 5, 7, 10, 12, 14 as my inputs. And if I rewrite my log function, it looks like that question mark, which is our base, to the y equals x. So picking one of my nice pieces, question mark to the 0 equals 1. Picking another nice point from my table, I see that 10 and 1, so our question mark base, our unknown base to the 1 equals 10. And we know that anything to an exponent of 1 is going to end up equaling itself. So that in turn tells us 10 to the first power is 10, which means that the base of this log button has to be 10. So let's go ahead and record that into our notes. So the log button on a calculator has an automatic base of 10. And you'll notice that the log button didn't actually write that base of 10, so that's going to be true both on your calculator and elsewhere. So if there is no base written in your log, that also means that the base is 10. Just like if we take the square root of something, there's no number written in that little elbow there, it's an automatic square root, right? So that invisible 2. And this is an invisible base of 10. All right, now we're going to go ahead and fully graph our log with a base of 10. And I already had my table, so I'm just going to use the points that were nice and exact, which was 1 and 0, and 10, 1. So it is increasing up and to the right, and it does continue decreasing down to the left there. So it's never going to cross that y-axis, and I want to be very, very careful with this one in our calculator because there is an asymptote right now at that y-axis, which is our line x equals 0. Because if we were to graph this in our calculator, so using our log button, which we know is that invisible base 10, graphing the log of x, and I'm zoomed out here, so let me zoom in. So you can see kind of right on that y-axis, it looks like my graph just stops, right? It kind of looks like a square root function. But if I zoom in, it's actually going to show me that it does continue down. It just gets closer and closer to that line, so it's hard to tell. So know that whenever we graph a log function, it will always have that asymptote. And so now we're going to try transforming our log function. So using our same idea of a, h, and k from all of our other function families that we learned in chapter 2, left and right, that was our h value, which always was with our x. So now before I do anything, I'm going to write down the 3 pieces of information that I know about my log base 10 graph, which is that I've got a point at 10, 1 and a point at 1, 0, and my asymptote is at x equals 0. So I'm going to go ahead and do that. I'm going to draw it as a dotted line, just as a reference point. So I haven't done any shifting yet. It's just there so that I can see and compare. All right, so let's say we are given the equation y equals log base 10 of, so that tells me what it is in that parenthesis, x plus 3. So I remember from all of our other functions that x minus h, right, that meant it was the opposite direction. So x plus 3 means I'm actually going to move to the left 3. So taking my one known point, moving it to the left 3, my other known point, moving it to the left 3. And so now, because of those 2 points, I can graph my shape, but I also know that my asymptote is moving left 3. So I'm going to draw that in first so that I've got the boundary there. And then connecting those 2 green points, increasing forever to the right, decreasing closely to that asymptote all the way, all the way to the left. There we go. That looks a little better. Make sure you have arrows on both ends as well. All right, let's try the other direction. Log base 10 of x minus 1. So that means I'm moving to the right 1. So I'm going to take all of my known points, moving them to the right 1. Same thing with my asymptote, that is going to move to the right 1. And once I have those 3 pieces of information, now it's super easy just to graph my shape again. All right, let's try up and down. Hopefully you remember that that is our k value, which is always on the outside. So log base 10 of x, and then on the outside, right, outside of the parentheses, it's not with the x, let's say plus 3. So that means I'm going to move up 3. So taking my point 1, 0, just moving it straight up 3, taking my point 10, 1, moving it straight up 3. And then my asymptote, if I move that up and down, it's just already a vertical line, so that doesn't change at all. And there we go. Now on the same graph, just because I don't feel like erasing it, y equals log base 10 of x, let's say minus 2. So again, based on my original, that white graph, I'm going to move those points down 2. My asymptote stays the exact same as it is. Since it's a vertical line, it will still be x equals 0. All right, our last 2, stretching and compressing. So that stretches our a value out front. So if it is a number that is greater than 1, that means it's going to be stretched. So 2 times log base 10 of x. Now if we think about our log whole function here, right, I'm just multiplying that by 2 to get my y value. So if I'm taking a look at my original points that I've got written over on the right side here, all that I need to do is take my y values and I'm going to multiply them by that 2. Right? I am stretching it vertically. That is your y variables. So my new points are 10, 2, and 1, 0. Right? Since 0 times 2 is still 0. And then I can go ahead and graph those. And my asymptote has not changed at all when I have an a value. So it is still on that line x equals 0, which is also our y-axis. Let's try compressing. So that means it is a number between 0 and 1. It's a decimal or fraction. So let's say 1/2 times our rest of our function, log base 10 of x. And I'm just putting brackets around that entire section because I feel like it. And same deal, I'm going to take the y value of the points, multiply it by that a value to get my new points. Because again, your a value is a vertical stretch or compress, which is only your y values. So I've got a point at 10 1/2, and then my point 10 stays the same. So it's increasing slower to the right, but that left still has that same shape. And by the left, I mean what's going down. And then my asymptote is in the exact same spot. All right, so let's record the information that we know about our log functions. So a parent log function, right? The parent just means that there are no transformations. So we've got y equals log base b of x, where b is some number. So in the parent function, right, we don't necessarily have the same exact b value every time. So it's just some number. Our general log function is now with our a, our h, and our k. So I'm going to start the same log base b of x, and then I'm going to go ahead and add my a value, which we know will stretch or compress my graph. I've got my h value, which is always subtracted from my x, and that moves it left and right. And then as a reminder, it is always the opposite direction as what it seems. So x plus something means to the left, x minus something means to the right. And our plus k on the outside is our up and our down. And just like our parent function, the b value is just some number, nothing specific. And there we go. That's transforming your log functions.